Hello friends, and let's talk today about the sum rule of the limits and of the derivative. So as you've seen in the previous video, we were able through the factor rule to put a constant factor outside of the limit, and tonight I'll show you how it's working for the limit of a sum. So first of all, let us consider the sum rule for the limits. So, well, remember, if we have a limit x towards 3, for example, of x squared plus x, we can basically substitute the x value for x. Here we're going to get 3 squared plus 3, which gives us 12. Alright, but we can also take it apart. We can produce limit x towards 3 of x squared only, plus a limit x towards 3 of x only, which would give us 9 plus 3, which is 12 again. So the question right here is, well, we have the limit of the sum and we have the sum of the limits. Is it always the same result? The answer is no. In this case, those two limits do exist, okay, and their sum exists as well. But let's have a look at the limit x towards 0 of minus 1 divided by x plus 1 divided by x, one of our bad boys. So, first of all, the limit x towards 0 of 0 is given, and now you see, well, it doesn't matter what x is approaching, we have a limit of a constant value, which is a constant value 0. So that's the story. But what will happen if we'll try to separate this and to compute the limit of minus 1 divided by x and 1 divided by x separately, and now you see we wouldn't be able to compute it here because those two limits, they just do not exist. So what's the question? What are the conditions for us to be able to put a limit of the sum into the sum of the limits? And the answer in this case would be that those two limits must exist. If otherwise they're not existing, we're in the trouble, like you see on this at this example. So the sum rule of the limits would say, if we have a limit x towards a of f of x, which is capital A, and if we also have a limit x towards a of g of x, which is capital B, then the limit x towards a of the sum f of x plus g of x would be equal to a limit x towards a of f of x plus the limit x towards a of g of x, if and only if those two limits are given, but this is the assumption, and that would be equal to a plus b. Once again, this is just a kind of definition, it's not a real proof or something. We're going to prove it differently once we are doing the real university mathematics with epsilon and delta. So no worries about that. But this is enough for us to understand the idea behind it so far, and now to use that in order to prove the sum rule of derivative. Let's do this. So sum rule of derivation. Well, let's define g of x, which is equal to f of x plus p of x, and those two functions are differentiable. So both are differentiable. What is the derivative g at xo? Well, you see, this is the limit h towards 0 by the definition, g of xo plus h minus g of xo divided over h. And now let's see what that would mean through our definition. So we just get f of xo plus h plus p of xo plus h minus, I open the parentheses, f of xo plus p of xo divided over h. Now we can solve the parentheses and we're going to get the limit h towards 0 f of xo plus h plus p of xo plus h minus f of xo and minus p of xo. We use the distributive law again, divided over h. Now we can use the commutative law and rearrange the sum. Look at this, we can switch the positions of those two. So we basically have f of xo plus h minus f of xo plus p of xo plus h minus p of xo divided over h. And now we can split this fraction into two pieces right there in the middle. So we get the limit h towards 0, f of xo plus h minus f of xo divided over h plus p of xo plus h minus p of xo divided over h. That's the story. And now we have the limit of the sum of two fractions, and as we've seen previously, we only can separate this sum if we know that those two limits exist. Do they exist? And the answer is yes, because the first fraction, this is the first principle, the differential quotient of the f of x function, which is differentiable by the assumption, and the second fraction is the differential quotient for p of x, which is also differentiable by the definition. So that means we have here a limit h towards 0, f of xo plus h minus f of xo divided over h plus a limit h towards 0, p of xo plus h minus p of xo divided over h, which gives us f prime at xo plus p prime of xo by the definition. Which means if we have, for example, x squared plus x, we can produce a derivative. If we separate those two, assuming they're both differential, but we already know the results of the derivation here, and that would be 2x plus 1. I hope it was clear. In the next lecture I'm gonna show you guys how to produce a derivative of the power function x to the power of n. We will kind of discuss, I would prove it later on with mathematical induction, but next time we're going to discuss it as I'm showing it, maybe the proper word for this, to my high school students. Alright, see you guys, all the best and stay healthy. Bye bye.